Hello friends, good morning. Hope you are all well. As we approach the last stage of the lockdown, I am looking forward to meeting you all in the university sooner rather than later. So far, we had interacted through the video lectures and WhatsApp and in the distance mode. But now we have gotten to a point where I think I would like to have some direct interaction with you, but let's see when that happens. Till that time, I would upload a few more of the video lectures like I have done so far. And today's topic will be some important concepts on statistical hypothesis testing and p-values, which I have introduced in my last two lectures. So today I am going to talk specifically from the chapter 10 named Hypothesis Testing and P-Values from this book, Larry Weserman, the All of Statistics, a Springer publication, which I believe many of you have access to as the soft copy. So if we briefly summarize, so we have been saying that there is a null hypothesis and an alternative hypothesis, and there is this data, and we look for evidence for or against the null hypothesis based on the data, and the evidence is summarized in the form of a test statistic. A test statistic is a function of the data. So a testing of hypothesis essentially involves choice of a test statistic. And now once a test statistic is chosen, then we have to compute the p-value. Now p-value I have explained with the help of an example in my last lecture, but the p-value is then compared with the level of significance. Now today I will talk about how do we compute the level of significance and something called the power of a test. So let me first explain the concept of power of a test. So I have said that in a testing of hypothesis there are two types of errors, namely the type 1 and type 2 error. What was the type 2 error? Type 2 error is probability of not rejecting a false hypothesis. The chance of that is let us denote it by beta. So let's say beta denotes the chance of not rejecting a false hypothesis. Naturally, we would like it to be minimized to as far as possible. Then 1 minus beta would be the probability of rejecting a false hypothesis. So that probability is called the power. So power is the probability of rejecting a false hypothesis, and we would ideally like it to be close to 1. Now a test is said to be most powerful if for a given level it has the power is maximum. Now how construction of most powerful test is a subject of great detail, which we cannot of course address in this talk. So first of all, I have defined the power. Power is the probability of rejecting a false hypothesis. And so to give an example, suppose I am testing a coin, testing whether a coin is fair or not. So p is the chance of getting a head. So null hypothesis p is half. Alternative is p not equal to half. Now suppose the coin is not fair, that is p is not equal to half. Then probability of rejecting the null hypothesis when p is not equal to half, that will be the concept of power. And but here one important point is, how do we decide to reject the null hypothesis? I have said that we compare p-value with the level of significance, but again p-value is not very straightforward to compute always. So in order to define the power or to define the level of significance, we need the concept of a critical region. So here if you look at this book, this critical region is being referred to as the rejection region, which you will find in the first page of chapter 10. So a rejection region is the set, it is denoted by capital R in this book in the equation 10.2, and it is defined as the set of all those observations for which the value of the test statistic exceeds some number c. Now this may be a bit hard to understand what I am exactly referring to, but let me try to explain that with an example. So if I am testing whether a coin is fair or not, then obviously the statistic of choice would be the number of heads in the observed tosses. That we know follows binomial distribution. Now if the null hypothesis is true, then we would expect the observed proportion of heads to be close to half. But if it so happens that in the sample we observe that the observed proportion of heads is away from half, then we have reasons to suspect. So our critical region in this case would be those trials for which the proportion of head is far away from half. So this is one example. So once we have a test statistic, we have to construct a critical region, and for that in statistics there is a lemma called Neyman-Pearson lemma. But fortunately we don't have to do this, because for most of the standard tests the critical region is well defined. So you don't have to take the chores to compute the critical region. Anyhow, suppose you have a critical region R, then what will be the power? Okay, before that, what is the interpretation of the critical region? That if your sample is in the critical region, then you reject the null hypothesis. That is why it is called the critical region or the rejection region. So now it becomes relatively straightforward to define the power. So power is the probability that your observed sample is in the rejection region under the alternative hypothesis. So this is the power. And similarly, the level of significance would be also easy to define now. It will be the probability that your observed sample is in the rejection region under the null hypothesis. So what we try to do is to determine the critical region in such a way so that the probability of type 1 error, that is the level of significance, is fixed at a desired level, say 5%. So that is how we fix the level of significance. I had told you that we'll fix the level of significance and compare the p-value with it as the benchmark. So I will explain it with the help of this concept with the help of a very standard test called the WALD test, W-A-L-D, WALD test. You will see in the subsection 10.1 in chapter 10. So I'll explain to you. Suppose I am testing a hypothesis regarding a population parameter theta. Theta could be anything, it could be the mean. And suppose the test statistic is denoted by theta hat. I am just reading from this book so that you can easily understand from this book. So I have a test statistic theta hat, and under the null, I am testing the null hypothesis that theta is equal to theta naught against a two-sided alternative, that is theta not equal to theta naught. So theta naught could be 0, for example, in your particular problem. So in this case, the test statistic is chosen to be the standardized value, that is theta cap minus theta naught divided by its standard error. The standard, now theta, every test statistic has a standard error. Why? Because it is a random variable, because its value changes from one sample to another. So you can compute its variance and hence you can find out its standard error. So if you look at this equation 10.5 in this definition 10.3, so there the WALD test statistic is defined as the ratio theta cap minus theta naught divided by its standard error. And the critical region is if the absolute value of this test statistic exceeds z alpha by 2. What is z alpha by 2? It is the alpha by 2th quantile of the standard normal distribution. So if absolute value of this w exceeds z alpha by 2, then you reject the null hypothesis. So what will be the power? Power would be the probability of this mode z exceeding z alpha by 2 when theta is not equal to theta half. And what will be the level of significance? The same probability, but with theta equal to theta half, theta equal to theta naught. And so this is one general testing procedure. A lot of tests fall under this category. For example, if you take your theta to be the population mean, and then this WALD test becomes what you know as the student t-test in the literature. So in that case, the theta hat would be the sample mean, and your standard error of theta hat, say, that will be the estimated standard deviation of x bar. Now variance of x bar is sigma square over by n, where sigma square is the unknown variance that you replace by the sample variance. So you get sample standard deviation divided by root n. So this world state statistic then becomes root n times x bar minus theta naught divided by s, where x bar is the sample mean and s is the sample standard deviation. So that is a very well known statistic called the student t statistic. So this is and in that case the critical region would be the student t mode of the student t statistics exceeding some typical some critical value. So this is how the concept of critical region is used to compute the level of significance and power of a test. So I will talk about more such tests in detail in my subsequent talks. But from now onwards, I would be more inclined to sending you typed material or referring standard textbooks, because beyond this, as you can see, it is getting a bit difficult to describe verbally. So take care of yourselves. Thank you.